Great, thank you, Anton. Over to you.
Yes, good afternoon, everybody, and thank you for the opportunity, Simon, to talk here. I'm sitting at Bruce's computer, so you might see Bruce's name up there. I also want to just issue this with a little bit of a health warning. It's still a work in progress. It's not finalized yet, but I would like to present some of the results and the processes that was followed. Zambili, can you just confirm that you can hear me well?
Yes, I can hear you clearly, Anton.
Thank you. Good, so just a quick overview of what we're going to be discussing, looking at the problem statement of the study, the layout, and the processing steps, and some conclusions. The problem statement that we looked at is, are machine data that are captured currently used to its full potential? And the question there is, what is actually being done with that? Is it used in management actively? And if not, why not? So one of the questions that came up was, can the data be trusted that we get from these machines? Lots of money has been invested in harvesting machines, like all of you must know, in the past decade. And a study by Venold showed that 60% of volume goes into Katuleng's system at the moment, or is harvested by Katuleng systems at the moment. Also, the Stanford data is captured on all machines, and the question is where that is then used. Simon has done a lot of work on this, and I know that there's a working group looking at this as well. So can we add credibility to these data, the data that has been captured by these machines? And we looked at an approach of using LiDAR then. The study layout is a study site at a New Scotland plantation of York, up in Mpumalanga. And there's an area that was demarcated for the study. Lots of other studies has been done at the same time. Simon looked at productivity of different machines and so on at the same time, but this is then 4 swaths or plots that was harvested by 2 different harvesting machines, Ponzi machines. And the points that you see on the screen is the actual GPS points logged by the Ponzi harvester at the time of harvesting. And the background shows the trees on each of those plots. At the same time, we also did a full scan of each of those plots with a terrestrial LiDAR scanner. So at the same time, manual measurements were taken, the DBH with diameter tape, as well as tree height with vertex. Machines logged diameter every 10 centimeters using the machine caliper, and the stem length by measuring with a machine measuring wheel. And then, as I mentioned, LiDAR was done on the whole plot using multiple terrestrial scanner locations. Each of them then registered to extract 3 parameters. This is an example of one specific scan, not combined scans, one scan, one single scan at a position, showing the trees in a grayscale, which indicates intensity as returned by the pulse from the scanner. The scanner that we used is a phase-based scanner. The other technology that's available is time of flight, in this case phase-based, with a full dome 360-degree scanning area, as well as, So from the scanning data, after the positions was registered, and I'll just show you a little bit about that just after the slide, there is a filtering algorithm that we run on each of the scans to remove points that are not valid. It's points that happen because of the movement of the trees, points that are ambiguous because of the scanner in integrity, or the scan integrity and on the scan. And those are marked in purple, blue in this case. And then the grayscale in this case indicates the distance from the scanner. So white the furthest away and gray the closest to the scanner in this specific picture. This is an example of what you get from the scan. This is a tree number 1. The numbers were marked with fluorescent paint or a white or a yellow paint on the tree. And at this specific position, you can then measure in the scanning software, can measure the diameter or the height of the tree. This is at 1.3 meters above ground height. So at DBH, the measurement 36 centimeters of the tree diameter at this specific position. You can also see in the background there's tree number 6 in the background, as well as tree number 10 or something in the background there. Targets were sticked onto some of the trees to help us register each of the scans so that we have then one single model for multiple scans. And this is an example of one of the targets. The blue triangles that you see on there is the actual position marked by the scanner software to find that target, and that it's the same target in 2 consecutive scans are then linked together to create a single model of all of the single scans. After the registration is done, there's still some problems in the registration. You can see 2 different scans here in this image showing the offset between the scans. You then run an ICP algorithm, an algorithm that looks at this cloud-to-cloud comparison and combine the 2 clouds in such a way that you have the least error between the 2 different scans. And this gives you a single indication of a specific tree. Single trees are then extracted from these scans, or from the model rather, the point cloud that results from this whole process. And the processing step involves thinning. So we typically remove some of the points to just make it quicker to run the algorithm. We remove isolated points above the point cloud or below the point cloud that happens because of noise, either in the scanner or overhead, birds, aeroplanes, whatever, flying close above the canopy. It creates points that can be removed. Also dust and rain and so on can be removed. And then also noise reduction to remove in general points in between the trees that are the result of dust or other things, so phenomena in the scan. So this is an example of one final scan that was imported into the R software then. Some of the filters applied to that, and then finally the thinning and the filters applied to that, so less points in the last one. From that, we extract the ground and normalize to ground to obviously get the accurate measurement above ground, DBH, diameter at breast height, and other measurements above ground. And then single trees are extracted. There's several algorithms that are run that can be used to do this. There's pipe models that you can run to get values from branches as well as stem diameters as a pipe. This is just a point cloud that is segmented to associate all points within a specific vicinity around the tree as a single tree, and each of them is then extracted as single trees. From that, we can calculate the height. In this case, one specific tree with a height of 23.9 meters. Other parameters can also be extracted, like ground width, height to the lowest, to the first live branch, and so on. Then finally, a circle fitting algorithm is run, and this is important because depending on the type of circle fitting algorithm that you get or that you use, you will get different results. In this case, an optimal circle fitting was run, finding the diameter of this tree at breast height, and the yellow line indicating the circle that was fit to the point cloud at breast height. So if we look at the comparison of the DBH distribution of what was measured by tape, by manual, by TLS, or the extracted trees from the point cloud, and then also by the point-C machine, we see some differences in the diameter classes. Basically, either under measurement or over measurement in the case of the TLS, under measurement in the case of the machine, and you have a shift in some of the distribution classes. If we compare that using statistics or just basic statistics, looking at the average size, and that would represent the average tree in this data set, in the full data set. Median tree maximum should represent the maximum tree in the data set, and the minimum, the smallest tree in the data set, and the total number of trees that were looked at in the specific comparison. What we do see here is that the population in terms of the TLS as well as the type is similar, and a slight overestimation with the TLS. In this case, median closer to the real value from the type. The maximum tree looks like it was the same tree, and the minimum or the smallest tree looks like it was the same tree in this case as well. A slight overestimation by the DBH of the TLS. That relates to the fact that you have the fitting algorithm, and if it takes the full diameter of the tree around the bark, in the case of the tape, you might be able to squeeze it closer to the tree, and there might be some smaller differences here, but it should be the same value. With a machine, we have underestimations in almost all of that, except for, there's an underestimation in all of the trees, and we accept that that is because of the pressure of the measuring wheel or the measuring wheel on the caliper on these trees. A comparison of the height indicates a slight underestimation of the TLS. That might be related to the penetration of the scan through the canopy. Specifically, phase-based scanners has less often a penetration to the top of the canopy than time-of-flight scanners. That has better penetration to the top of canopy. Also, the distance. The distance that I've used to cut off in the scans was 50 meters, and it depends on the angle that the tree is. If a tree is 10 or 20 meters away from the scanner, I might have filtered out some of those points to create the full tree canopy above, or at least at tree height. So here we see a 4 meter underestimation on the maximum. The average and the median was sort of similar, and the small tree, you can also see the lowest value here that is close to the value that was measured by the vertex in this case. So some of the preliminary conclusions that we have from this data, and as I said, it's still in the process of finalizing, is that we have problematic measurements of top of canopy heights. The idea was to, in the beginning, also get a drone flight of the same compartment, but with several problems on the day. We couldn't get a final flight, or the data that we got, we could not analyze to get a top of canopy representation using the drone, or photography rather, to replace the top of canopy from the TLS. As I said, time-of-flight scanners might be able to get better penetration and provide better results, but we only had a phase-based scanner on this day. The diameter circle fitting algorithm is important in the selection of this algorithm to find the best solution of estimating the diameter at breast height, as well as diameters in the rest of the tree. With the machine data, it's important to look at the setup of the Stanford D data and the records that are locked at the time of harvesting, as well as the calibration of the machine caliper is important. And then also looking at some of the results, over and under bark estimation is related to the bark factor that is used in the machine rather. And one would also have to take into account the pressure of the rollers as well as bark loss that happens at the time of measurement, which could get underestimation of the diameters of the tree. I mentioned the bark factor. That's something that needs to be updated still, and we will do some work with this because we can basically estimate underbark as well as overbark from this data set, and then provide maybe a better indication of the bark factor from this data. I would also like to thank York Timbers and the field staff of York on the day for helping with laying out these plots and doing the scan of the data, and also Bruce Talbot and Simon Ackerman that was leading the study actually, and I'm open for any questions.